All right, so on page 14, we're looking at number 11. So for this problem, we have division. All right, so we would apply the quotient rule. All right, so I'm going to abbreviate that QR in a minute anyway. So this would become log base b of s to the 4 over 7 minus log base b of u to the 7th. Okay, so we're applying the quotient rule for that, the QR. All right, so if the entire expression is contained within the logarithm and that expression involves a quotient, you would apply this rule. All right, then we could apply the power rule. Right, abbreviations will be a little dangerous here because PR for power rule could also mean PR for quotient rule. So I'll show you how I'll write that in a minute. It's not like you need to justify your steps. It's more so I just want you to have access to what steps were applied. All right, so 4 log base b of s minus 7 log base b of u. And we're going to call that the POW rule. All right, and that's as far as you can go, because once you have a single argument contained within the logarithm, all right, so just a single letter or a single number, the properties are done. The only thing you might be able to do, sorry about that, the only thing that you might be able to do is run it through the calculator, but when you have a base of unknown b, there's nothing you could do there either. Right. 13 is a little beefier, but it's got the same general structure. So we'll start off with the QR. So log base b of m to the 5th, n to the 3rd, minus log base b of the root of p. Again, quotient rule. There's an implied multiplication here, so I could use the product rule. So to make this log base b of m to the 5th plus log base b of n to the 3rd, bring along the log base b of the square root of p, but I'm going to write that square root of p as p to the 1/2 power. All right, that's a old algebra skill. If I have something like the square root of 9 versus 9 raised to the 1/2 power, they're going to give me the same thing. All right, so I applied the power rule, the product rule here. Now I'm going to apply the power rule. All right, so I'm going to make those exponents hop over the log. For each one of those logs, each one has its own exponent. So jump each one of them. So 5 log base b of m plus 3 log base b of n minus 1/2 log base b of p. And again, that was the power rule. All right, again, the rules, I'm just writing them on the side for your benefit. Bottom line is, as long as you can get to the simplified form, then you're good to go. All right. I don't want people walking away thinking, oh, now I have to show all the steps too, show the steps and the reasons for it. Not necessary. All right. Numbers 14 and 15 are some of the trickier ones, right? Because you see an exponent here, and you're like, oh, I'll just apply the power rule. The problem is, that exponent only applies to the x to the base of x. So x to the 2x power, that 2x power is only applied to the x. Right? So I'm going to take a little multiplication symbol and tuck it in there and apply the product rule. So log base 2 of 2 plus log base 2 of x to the 2x power. All right, that's again the product rule. All right. Now, it's very easy to lose track of this, but this is a base of 2, not a base of b. So this is something that I could get a numerical value for. I could do it if you happen to remember that if the base and the subject of the log are the same, the result is equal to 1. That's great. I always look at it when it comes to logarithms. This is my base. I want to see what I would have to raise this number to in order to get this number. So 2 to what power equals 2? 2 to the first power is equal to 2. All right. So that's a way to reason it out. But in a pinch, go into my toolbox. You see that? Oops. See that little log base a of x? Hit OK on that. Put in a 2 here. Put in a 2 here. And you have the answer. All right. For the second part, I'm going to hop that exponent over the log. So this is going to become 2x log base 2 of x. So I applied the power rule. All right, and there's nothing I could do beyond this. This is a variable, so it's not like I can chuck it into the calculator. And it is just a simple single-termed expression. You know, basically, I want that to be as bare as possible. So you could have a variable in there, you could have a number in there, but it should only be the variable or just or the number. So think of it this way: that x is 1x to the first. Right? That's how we want it to be structured. If I have a c in there, 1c to the first. No coefficients, no exponents, because we have a rule to handle those. Right? This one's same idea, except with a natural log. So again, I'm going to tuck in a multiplication. So this is going to be ln of 5 plus ln of x to 2x. So I applied the product rule. I'm then going to apply the power rule. Now that ln of 5, you could chuck that into the calculator, but it's going to give you a pretty gnarly looking decimal. I'd rather have the ln 5 than the gnarly looking decimal. So I'm going to leave this as ln of 5. So plus 2x ln of x, and again that was the power rule. All right. When it comes to logs and decimals, you really only do it when a question asks you to do it. All right. See the next little section here: solve each equation and round answers to 4 decimal places where necessary. So it may not always be necessary. For this one, I'm going to use the circular approach. I'm going to take the 2, raise it to the negative third power, and that's what x is going to be equal to. This is the technique that we would use if there is a variable contained within the log. The idea being is I want to release the variable from the log so that I can figure out what the variable is equal to. All right. So 2 to the negative third power, 1/8. That's a nice clean answer, so I'm just going to say x is equal to 1/8. Just be careful with domain. For a log, you can't take the log of a negative number, and you can't take the log of 0. I'll give you an example. Log of 0, undefined. Log of -1, or non-real. Natural log of 0, undefined. Natural log of, let's say, -5, non-real. All right. So if the x value that you get when you solve the equation makes the log undefined or imaginary, non-real, then we would dismiss it as a possible answer. All right. It doesn't come up very often, but when it does, it's impactful. All right. Number 17. So here what I want to do is I want to condense into a single logarithm so that I can just see what the difference is from the left side of the equation to the right side of the equation. So this is going to be the reverse of the power rule. I'm going to write this as log base 5 of 4 times x. and that's equal to log base 5 of 36. I think I said power rule, I meant product rule. All right, so product rule. All right, so now the only thing that varies from the left side of the equation to the right would be the subject of each logarithm. If I could figure out the value of x that would make 4x equal to 36, then I would have equality. So 4x equals 36, meaning x has to be equal to 9. All right. It's a little bit of a lengthier process to do it in the calculator, but it'll also give you the answer. So let me just show you that real quick. So if you go to equations, well, we don't need this. I'm going to select empty. I'm going to use the log with the base 5 of 4. I'm going to put the original equation in there, plus log base 5 of x equals, so shift pi to bring up the equals, log base 5 of 36. Go to solve the equation. I already know the answer is 9, so going from -10 to 10 will work, but if I wasn't sure, I would do something pretty wide, like -100 to 100. That would cover more of the field. All right, so then I hit enter, OK or execute, and I get my x equals 9. All right, so you can do it that way too. If the answer exists in the domain that you select, then great. But let's say I did -5 to 5 as my domain, it'll say this. That just means I have to widen my interval. All right, so that's an option. For this one, number 18, I'm going to divide both sides by 75, just to kind of make it a little tidier. 1000 divided by 75. Not the nicest looking decimal, so I'm going to leave it as a fraction. 40/3 is equal to e to the 0.5x. You can convert this to a log, or you can take the log of both sides. Now you have a choice: common log, log, or natural log, ln. We use ln if the base is e. All right, because there's some nice properties of natural logs that'll help us out. If you take the natural log of one side, you got to do it to the other. So it's natural log of this, natural log of that. On the right-hand side, I can hop the log with the exponent. All right, so I'm applying the power rule. So I have ln 40/3. You can put parentheses or not, it doesn't make a difference. As long as it's clear that that 40/3 is part of the natural log. So 0.5x ln of e. Now if you don't know it, that's fine. You could type it in the calculator, ln of e, and it'll spit out a 1. But that's the reason why we selected a natural log, because the natural log of e is equal to 1. I'm able to cancel that out. All right, so I have ln of 40/3 is equal to 0.5x. I'm going to multiply both sides by 2. And that'll give me a final answer. 2 ln 40/3 is equal to x. Let me just put the 2 in there. So I can leave it like that, or if the situation calls for a decimal. Now here, you could go either way, but just to get a sense, 2 ln 40/3 is approximately 0.5754. But this is actually, believe it or not, the nicer answer, because this is exact, this one isn't. All right, number 19 looks pretty gnarly too, but if we apply some properties to simplify it, we can we can clean this up rather quickly. All right, so I have subtraction, so that's going to be my quotient rule. So log base 6 of 216, and actually before I even do that, let me take this coefficient and make it an exponent. So let me erase this. I'll rewrite the line, I don't want it to be too convoluted. So log base 6 of 216 minus log base 6 of 36 to the 1/2 is equal to log base 6 to the x. So this is the power rule. Now I'll apply the quotient rule. So log base 6 of 216 over 36 to the 1/2 is equal to log base 6 of x. All right, now the only thing that varies from the left side to the right side is the contents of the logarithm. So I could take that 216 over 36 to the 1/2 power and set that equal to x. All right, now we could also clean it up a little bit. So 216 over 36 to the 1/2. Now 36 to the 1/2 is the same as the square root of 36, which is 6. So you could actually just kind of cut out some of the fluff there, but you could also just type it in as is. Either way, you should come up with x is equal to 36. Ooh, that moved on me. A little resize action here. And again, I'm just going to make a note that I applied the quotient rule. All right, so it takes a little getting used to, but it shouldn't be that bad. Number 20, no coefficients, so I'm not worried about power rule, but I do see a product, a sum here, so that's a product rule. So log, they didn't write a base, so that must be a base 10. I'll make a little note of that. Of x plus 10 times x minus 5 is going to be equal to 2. All right. Now I can convert over into exponential form. So, you know, that little circular approach. And yeah. So we're going to write this as 10 to the second power is equal to x plus 10 times x minus 5. So now we're done with the log, which is great. I do have to solve the quadratic though. All right, so 100 is equal to, I'm going to distribute this out, x squared minus 5x plus 10x minus 50. I'm going to combine these two terms, and I'm also going to subtract 100 from both sides. So I'm going to have 0 equals x squared plus 5x minus 150. I'm going to factor 150. I'm thinking 15 and 10. If the 15 is positive and the 10 is negative, that'll give us the 5x in the middle, so we're good. So we have x is equal to negative 15, or x is equal to 10. Now I just got to make sure that these are going to work inside the logarithm, meaning it's not going to generate a negative number. So if I replace the x here with a negative 15, I'm going to get negative 15 plus 10, which is going to be a negative 5. Log of negative 5 is one of those values that's imaginary, right? So that's bad news. I could run through with the 10 and have no problem whatsoever, but the 15 is going to cause it to be undefined, so we reject it. All right, so you got to be careful about stuff like that. But if you're in doubt, go into your equation app, type in the original. So log, this will be a little easier to type in because it's a common log. Log of x plus 10 plus log of x minus 5 equals 2. Solve the equation. Now my x min, x max, like let's say I actually thought that that negative 15 would be a solution. It wouldn't show up in the window that I have here. So let me make that a little wider. I'll go negative 100 to 100. So by a little wider, I mean a lot wider. Hit OK, and it only brings back the 10. It did not bring back the negative 15 because it's not a solution to this problem, even though the algebra made it seem that way. Number 21, we have a couple of QRs here, 1 and 2. So log of x over 5 is going to be equal to log of 2 over x minus 3. So again, that's the quotient rule. So the only thing that differs from left side to right side are these two expressions. So I'm going to pull that out and solve this proportion. So a little cross multiply action. X times x minus 3 is equal to 10. Distributive property, x squared minus 3x equals 10. I'm going to bring the 10 over. X squared minus 3x minus 10 is equal to 0. Factor x and x. Thinking 5 and 2 to get me to a 10. So if it's negative 5 and positive 2, that'll multiply to negative 10, but then also add to a negative 3 and a negative 3x in the middle. So I get x is equal to 5 or x is equal to negative 2. I'm just going to have a quick look back to my original equation. If I plug in a 5, I'm good. All right, so if I plug in a 5 for x, log of 5. All right, if I plug in a 5 for x here, log of 5 minus 3, so log of 2. Those are good numbers. All right, now if I plug in a negative 2 for x here, I'm going to get log negative 2. It's going to say non-real answer. All right, so that negative 2 is no good. So I'm going to toss this one and reject it and only keep the other one. All right, now on page 15, we have a few problems there. These are word problems related to exponentials and logs. So one of these 4 formulas are going to be applied. If you're talking about money, you're most likely talking about compound interest or continuous compound interest. Right? So it's the context that's going to drive it. So let's take a look at number 22. Anthony is a financial advisor working for a corporate pension fund. He needs to have 14.6 million grow to 22 million in 6 years. What interest rate to the 100% compounded annually does he need for this investment? All right. So compounded annually, number of compound, oh, that's not a highlighter. Number of compounding periods. All right. So I'm going to use A equals P times 1 plus R over N to the NT power. These other ones don't reference money. So it's one of these two, but because it's compounded on particular intervals, it has to be this one. All right, so we want it to end up being 22. It's right now 14.6. You don't have to put the millions in there, like 22 million, 14.6 million, because those 6 zeros are going to cancel out anyway. All right, so 1 plus, we don't know what R is. They told us that N, indirectly, told us that N is equal to 1. And that's because annually happens 1 time a year. Raised to the 1 times 6 years. Compound interest formulas, the time value is always measured in years. If it's not compound interest, it's depending on the rate. All right, whatever units are in the rate, that would dictate the number of whatever the units of time would be. All right, so I'm going to divide out the 14.6. I'm going to clean it up a little bit. So I'm going to leave it as 22 over 14.6 is equal to 1 plus r raised to the 6th power. All right, if I want to undo a power of 6, nothing fancy, just take the 6th root of both sides. So I'm going to get 1 plus r because the root of 6 and the power of 6 cancel away. And I have this not so pretty looking expression. I'm leaving it in this form because I'm going to put it all in the calculator anyway, and I don't want to have to worry about rounding just yet. All right, so subtract 1 from both sides. Cancels here. They're not like terms over here, so I would write this as, just do a copy paste here, this expression minus 1, and that's what r is going to be. All right, so let's get that into the calculator. So if you need a root other than a square root, you could do it by raising to a power of 1 over 6. Or if you go into the toolbox, you see the nth root, select that, type in 6, and I want 22 divided by 14.6 minus 1. So it's that number, but they said to the nearest hundredth of a percent. All right, so don't lose sight of what the question's asking for. All right, so r is going to be approximately, I'm going to multiply this by 100, so 7.07%. All right, that's a pretty big interest rate. I haven't seen 7.07 in my lifetime. Of course, you know, prior to like 20, 30 years ago, I wasn't looking, so I don't really know, but that's a very large interest rate. Number 23. How many years to the nearest year will it take the population to double if it grows continuously? All right, so continuous exponential growth or decay. We're not talking about money here. So I want this formula. N is equal to n sub 0 e to the kt. That little subscript of 0 just means when time is equal to 0. So it's initial. All right. Doubling is a 2-to-1 ratio. I could put in whatever I want. I could put in 100 for the initial value and 200 for the final value. I could put 75 for the initial value, 150 for the final value. It doesn't matter. It's always going to be a 2-to-1 ratio. So I'll just put in a 1 for the initial and 2 for the final. All right. So cleaning this up, I could write it as e to the 0.02t is equal to 2. To release a variable from an exponent, one approach that I could use would be to take the natural log. And again, the reason it's natural and not common is because of the presence of a base e. All right, that allows me to hop the log. So this 0.02t comes down and becomes a coefficient. So 0.02t ln of e is equal to ln of 2. ln of e, we talked about this before, cancels to a 1. So now I have 0.02t equal to ln of 2. Now I can just divide both sides by 0.02. How many years to the nearest year? So cancels on this side. I'm just going to chuck this into the calculator. ln of 2 divided by 0.02. So we get t is about 34.6574, but it said round to the nearest year, so about 35 years. All right. Once you come up with an equation, if you want to go to the solver in your calculator, you can. It's the algebraic approach that I'm choosing to do here, but you can go either way. All right. Number 24, local bank offers a CD that pays 1.8% interest compounded continuously. All right, compounded continuously is A equals P e to the RT power. Takes out a 1 year investment, so T is equal to 1. 1.8%, so 0.018. And he's starting off with a P value of 5,000, and we want to know what the final amount is going to be. So 5,000 e to the 0.018 times 1. So this is just plug and chug. E to the 0.018. You can put the times 1 in there if you want, or just leave it off. It is going to become, let's see, rounding doesn't say. So $5,090, and I'll say 81 cents because we're talking about money, so it's not an unreasonable way to round. So after the 1 year, he'll have gained $90, right? Because 5,000 of that is what he started with. How much will the investor have in the account? So they want the full answer, but sometimes they could say, how much would he have earned in interest over the time? Number 25, determine how much time to the nearest year is required for an investment to double if it's compounded quarterly. Quarterly, so A equals P times 1 plus R over N to the NT power. All right, so we use that formula. We don't know the time value, but we do know that it's going to double, so 2-to-1 ratio. 1 plus 0.0575. That's the interest rate in decimal form. Oops. Quarterly means it happens 4 times a year. 4 times T. All right, so I can clean this up a little bit, but not a whole heck of a lot. So 2 is equal to, inside the parentheses, 1 plus 0.0575 divided by 4 ends up being that decimal. It's a little lengthy, but it's not terrible. So 1.014375 raised to the 4t power. Like I said before, if I want to get a variable out of an exponent, I can take the log of both sides. Since I've been doing it with a natural log, I'm going to keep doing it with a natural log. Apply a natural log to both sides and use the power rule to make the exponent into a coefficient. All right, so then that's going to give me ln of 2 is equal to 4t ln monstrosity of a decimal. If I want to get the t alone, I can divide both sides by first the 4. That would cancel here, so divide both sides by 4. But then I could also divide it by ln of 1.014375. That's also going to cancel on the right. Oops. Cancel on the right, and it's just going to leave me with the value of t here. Right? So whatever this quotient is, that's going to be pretty much my answer. So I'm going to say ln of 2 divided by 4 ln 1.014375. And so t is going to be about, said to the nearest year, but I like to put the full decimal there first, or at least a fair amount of it. So this is about 12 years. All right. And then number 26, the number of guppies living in logarithm lake doubles every day. If there's 4 guppies initially, express the number of guppies as a function of time. So that's just straight up exponential growth. So n is equal to n sub 0, 1 plus r to the t power. Right? If you're doubling, you're increasing by 100% of your value. So let's say I have $5. If I double that, I have $10. I've increased the $5 by 100% of its value. Right? So long story short, when we're talking about doubling, the R value has to be equal to 1. All right? It says to do it as a function of time, so they're telling me that I don't know what the value of time is, so that's fine. We're starting off with 4 guppies. 1 plus 1 to the t power is equal to n. So n is equal to 4 times 2 to the t power. Now that 2 is being raised to the t power, so do not multiply the 4 and the 2. So if you came up with n is equal to 8 to the t power, that is absolutely not correct. So I'll put a little cautionary stuff going on here. But that's going to be my function, this. Just leave it as is. If you're ever in doubt, if you think that maybe you're not allowed to do whatever it is you're about to do in terms of simplifying, just don't do it. All right. Now it wants to know how many are in the lake after 1 week. 1 week is 7 days. All right. The rate of change is associated with days. All right. So what I need to figure out is n of 7. 7 days. 4 times 2 to the 7th power. Use your calculator. 4 times 2 raised to the 7th is going to be 512. Units are important, so 512 guppies. Don't just put 512. You haven't answered the question if you just put 512. All right, how many guppies? 512 guppies. All right. To the nearest day, when will there be 2,000 guppies? So that's saying n is going to be equal to 2,000. If we know n is equal to 4 times 2 to the t power, then we could set this equal to this. All right, so 200 is equal to 4 times 2 to the t. I could divide out the 4. So 500 is equal to 2 to the t power. Again, I have variable trapped in the exponent. A way to release it from captivity is apply a log to both sides. So that t can now hop over the log and give us ln of 500 is equal to t times ln of 2. Divide out the ln of 2 and you'll have your answer. All right, so just run that into the calculator, run it through the calculator, I should say. Cancel, cancel, oops, cancel, cancel. ln 500 divided by ln of 2. Nearest day. So t is about 8.966. So it's about 9 days. Then the last thing is to produce a graph. So it's a graph of this function here. All right, so, and as you know, the overarching theme of this course when it comes to graphs is they're just sketches. All right, so n is equal to 4 times 2 to the t power. N is taking on the role of y, t is taking on the role of x. So instead of the xy axis, I'll say the t and n axis. We can just plug in some test values, or you could type it in as a graph and plot some points. Either way is fine. All right, so if I put in a t value of 0, if I make this 0, 2 to the 0th power would be 1 times 4 is 4. All right. It's increasing, so we know it's going to have a look like this. I could plug in a 1. If I plug in a 1 for this, 2 to the first power is 2 times 4 is 8. So 5, 6, 7, 8. It's going to go off the rails after that, but we know it has to be asymptotic with the x-axis or the t-axis, so it has to start off fairly close to the t-axis and then increase through these points. And once you do that, you have your graph. But like I said, if you want to just type it in to the grapher, get rid of this. Y equals 4 times 2 raised to the, we'll say x power. And then go to the table of values and grab some points. It doesn't default to negative values. I have this set up from something I did in previous class. So I would set the interval to go from -10 to 10. I don't need to go by half units. I can go by units of 1, hit OK, and now I have a bunch of points. I only really want the clean ones. So at -3, it's half a unit. -2, it's 1 unit. -1 is 2 units. You could plot all those points if you want. But you see after 1, it goes off the rails pretty quickly. All right. You really only just need a couple of points and an understanding of what the overall trend is. All right. So Newton's law of cooling states in part, because there's a lot more to it than this, but this is all we need it for, that when an object is left in surrounding air that is lower temperature, the object's temperature will decrease exponentially, leveling off as it approaches the surrounding temperature. Very important. I mean, very important in terms of physics, but not in terms of math. Newton's law of cooling it's called the law of cooling, but it's really that the temperature of an object is going to approach the temperature of the surrounding medium, right? So if I take a cold piece of chicken and put it in an oven that's at, let's say, set to 200 degrees, eventually that piece of chicken is going to have a temperature of 200 degrees. It'll never go to a higher temperature than the surrounding medium, right? Same idea for cooling. If I take something out of the oven, like a pie, the lowest temperature it'll ever get to is the temperature of the surrounding medium. It's not like you could take a pie out of an oven and leave it there for 20 hours and expect it to be an ice cube afterwards. If the temperature of the air around the object is 60 degrees, 68 degrees, 70 degrees, whatever, that's the temperature that it's going to approach. That's kind of neither here nor there. It's more like, all right, we have a formula. We can use that formula to answer some questions using pre-calc concepts. All right, so it's capital T of lowercase t is equal to AE to the KT power plus TS, T sub S. The lowercase t is time, so it's temperature as a function of time. And that's going to be equal to some coefficient, and we'll solve for that coefficient. E, which is Euler's number, is about 2.718, raised to the KT power, all right? K is a constant. It represents a rate of cooling, all right, or increase in temperature, but we're only focusing on cooling, right? A is the difference between initial temperature of the object and the temperature of the surrounding medium, all right? And by the way, you're not expected to know, like, if there's a word problem on the test related to exponentials, it's not like you have to know this information. It's more like you just need to plug into the formula correctly. You'll be given this information if it's relevant on the test. And also, the way I treat tests in a remote environment is that they're pretty much all open notes, right? So you will be able to access your notes while taking the test, all right? So that's not out of bounds. The only kind of stuff when it comes to test taking that's out of bounds is anything else that would be considered cheating, like emailing a tutorial service and having them do the work for you, or communicating with a classmate. If your work is your own, then the resources that you could use are, they're, I don't want to say unlimited, but there's a fair amount that you could use, because it really is just a matter of like looking for a similar problem that maybe we completed previously, or like just referencing some notes, whether it's a definition or something like that might help you figure things out. All right. So, like I said, this formula is really just for the sake of us being able to practice our skills associated with logarithms, etc. All right. So a pot of warm soup with an internal temperature of 100 degrees Fahrenheit was taken off the stove to cool in a 69 degree Fahrenheit room. After 15 minutes, the internal temperature of the soup was 95 degrees Fahrenheit. All right, so it is cooling. It's not cooling very fast. All right, but we'll kind of bear that out in a second. All right, so A, like the capital A coefficient, is the difference between the initial temperature of the object, which is 100, and the temperature of the surrounding medium. All right, that's the room. I'm going to go green here. So internal temperature, the room. So 100 minus 69 is going to be equal to 31. All right. So I could start building my formula. T of T is going to be equal to 31 e to the kt power plus the temperature of the surrounding medium, which they told us was 69. All right. So if we could figure out the value of K, then we'll have enough information to answer the following, the questions that follow. All right. They tell us that after 15 minutes, the internal temperature of the soup was 95 degrees. All right. I'll go yellow for that. After 15 minutes, internal temperature was 95 degrees. All right. Part B is saying to the nearest minute. Part C is saying what'll happen after 2.5 hours. So there's kind of a disagreement in terms of the units of time. So we will decide which way to go in terms of those units. All right. So when we say 15 minutes, we could say 15 minutes, or we could say 0.25 hours and work in the units of hours. All right. So I'm going to let T be measured. I'll just say B. In hours. Like kind of stuck in a corner here. Clean that up a little bit. Let T be measured in hours. Handwriting's a little iffy this evening. I tried to remount my, I have a wall mount for my iPad. I tried to remount it. Now it's kind of wobbly, and therefore my handwriting is a little wobbly. All right. So T of T, so 15 minutes. So temperature after 0.25 hours is going to be equal to 95 degrees Fahrenheit. All right. So what I can do is apply this T of 0.25 to the function, replacing the instance of T, lowercase t, with a 0.25. Now that's supposed to be equal to 95, so I'm going to write 95 equal to all this stuff I just wrote. All right. So now I want to solve for the value of K. It's a variable exponent, which means we're going to involve a logarithm in a minute. But before I do that, we'll take care of the easy stuff, which is, let's get rid of that 69. I'm going to bring the results up here. 95 minus, oh, that's an 8. Minus 69, talking 26. That's going to be equal to 31 e to the 0.25 K. All right, I'm just adjusting a setting here. All right. So now I want to get that 31 out of there. So I'm going to divide both sides by 31. So 26 over 31 is equal to e to the 0.25 K power. One strategy to get a variable outside, get it from an exponent to something that's not an exponent, would be to take the natural log of both sides. So I'm going to say ln of 26 over 31 is equal to ln of e to the 0.25k. The reason why we do that is because we can apply the power rule for logarithms, which is to say, I'm going to take this exponent and hop it over the log, and I'll end up with, at least temporarily, the natural log of 26 over 31 is equal to 0.25 k times ln of e. Now, you may not remember the property, but the calculator does. So if I type in ln, so hitting that ln key, just do that again a little slower, ln, and then type in e. So alpha, comma brings up the e. Hit enter, you see that that's equal to 1. All right. And what that means is that this is going to cancel away. So now I have, I'll write it this way, 0.25k is equal to ln of 26 over 31. I could divide both sides by 0.25, or a little bit more conveniently, I can just multiply both sides by 4. So 4 times 0.25k, and then multiply by 4 over here, you're going to end up with k equal to 4 ln 26 over 31. We're not going to actually multiply the 4 by the argument, the 26 over 31, because that's contained within a logarithm. So we got to kind of look at those as not like terms. So 4 would just become the coefficient of the natural log. All right. Now, it seems like a year ago when we first started this problem, but I can now put this k value in to the function and get an equation that's going to work to help us solve the rest of the problem. So t of t is equal to 31 e. I'm going to bring this down a little bit, give myself a little bit more room. K, so 4 ln 26 over 31 multiplied by t plus 69. All right, that's a lot of work to get, you know, an equation that's not the prettiest, but it is effective. I mean, and there's more simplifying that can be done, but it's not necessary because we have enough to be able to answer the remaining questions. So all of that was part A, but part B and part C are now going to be really quick because we have a formula to work off of. All right, so for part B, let me just grab this. Oops. Hold on. Come on. There it is. So this is my function. I'm going to set it equal to 80 degrees Fahrenheit. So I'll just say 80. And now we have an equation that we can solve. Now it's up to you how you want to solve it, right? We can make this, we could do this the easy way, or we could do it the hard way. All right, the easy way is going to be to get the calculator involved. The harder way is, well, you guessed it, not getting the calculator involved. So I'm going to set up both parts B and C and use that to help me get my answer. For C, it says to the nearest degree, what will the temperature be after 2.5 hours? All right, so that's lowercase t is equal to 2.5. So I'm going to figure out t of 2.5. All right, but again, not an algebra course. So let's get the calculator involved. So hit the home button. All right, so home. We're going to go to, you could do it one of two ways. Let's start out, we'll do it in the order that the question appears. So I'm going to go to equations. All right, so equations, hit OK. And now I'm going to just put in this equation. All right, just the way I see it. All right, so if it looks in the calculator display the way it looks on paper here, then we're in good shape. Hit OK.
Professor, so sorry to interrupt. I have a question. On
Sure.
the formula, is it like 26 over 21 or 26 over 31?
Over 31.
Oh, because it looks like a 21, or is it because it's small?
It's
Oh,
because
got
of
it.
my terrible handwriting.
Oh, thank you. Okay.
Thank you. All right, even over here, it's like it's merged into kind of nonsense, but yeah, it's intended to be a 31. All right, so I'm going to hit OK to pop the equation in. So 8, 0 equals, we do that by hitting Shift, pi, type in the 31. Then I need the E raised to a power. If you look carefully over right below Shift, there's an E with a built-in power function. All right, so a power, tool, I guess. I'm going to type in 4 ln of 26 over 31 t. All right, so it takes a little doing, but parentheses 4 ln 26 over 31. Close it up. Now, it says t. I could use t or I could use an x. It doesn't make a difference. Since it's more convenient to hit x, I'm going to do that. All right. That, it doesn't look pretty, but it's in there correctly. Now I just have to put the plus 69. All right, so I'm going to hit the right arrow so that it grows up and becomes a ordinary size font. Plus 69. All right. So yeah, the character size when it comes to numworks, it's a work in progress because subscripts should be a little bit smaller, but they seem to go with the same size no matter where you put it. All right, so I'm going to hit OK. It's going to lock that in. And then I'm just going to go to solve the equation. All right, so I hit OK on solve the equation. It asks me if the window that I have here, or I'm sorry, the domain of -10 to 10 is what I want to do. Well, it's a measure of time starting the moment the object is taken out of the oven. There's a pie or something. Oh, no, warm soup. So I don't think my X min should be anything less than 0. So I'm going to make this 0. And honestly, I don't know how long it would take for the soup to cool down to 69 degrees, but just using, I'll call it common sense, but you make a hot cup of coffee in the morning and you put it out on the counter, like if you take a sip out of it after 30 seconds, you're probably going to burn yourself. But if you wait 5 minutes, it's going to maybe be a little bit more tolerable. If you wait 2.5 hours, it's going to be whatever the temperature is in the room. All right. So you got to figure not too much time is going to go by before this thing reaches that temperature. But 69 degrees is, if you try to keep your place at a comfortable temperature, you're probably living in the 65 to 75 degree realm, unless you like it warmer, in which case maybe you go up to 80 degrees. But, it's not going to take a whole heck of a long time to get down to that temperature. So it had, as it stands right now, it's at 10 hours. I don't know that I need 10 hours. So I'm going to change that to a 5. I don't know that I need 5 hours, but I'm going to do that anyway. I want to keep it, a nice round number. So I hit OK on solve the equation, and it gives me the value. If it says no answer found in interval or words to that effect, then you chose a poor interval, right? But here I have, about 1.473 hours. It says to the nearest minute. So I want to take that number and multiply it by 60. 60 minutes in an hour. Now, in NumWorks, if you go right onto the number and hit Shift var, it'll copy it. And then we just go right back to the home screen, Shift toolbox to paste. So it's copy paste. You just got to look to see where the copy is. It's right above var. You could also cut. It's not always necessary, but either way, copy paste times 60. And we have, about 88.358 minutes. All right. So it's going to take, almost an hour and a half to get down to room temperature, which is probably good, I guess, reasonable. If you have some hot soup and you leave it out on the counter, you don't want it to be room temperature after like 10 minutes. It's not going to be good. Like it might be edible, but it's not going to be as enjoyable as it would be if it were a little bit warmer. Right. You also don't want it to take like 20 hours to get down to room temperature, because that would mean like after an hour, it's still scalding hot. All right. So, a lot of different ways to kind of conceive the meaning of this, but it really is, it kind of falls into the realm of common sense. For the second part, it's just substitution. So I'm going to take that 2.5 and I'm going to put it into my equation for t. You can do that right in the home screen. It just unfortunately means that you're going to be doing a little bit of repeat typing. However, if you go back into equations, you can copy paste by hitting Shift. So holding down Shift, hit the left arrow until it slides over the value that you're trying to copy paste. Right. The thing is, on the emulator, it's not going to work. It's kind of annoying. But if you hold down, like on the hand, if you have a handheld, you hold down Shift and hit the left arrow, it'll highlight, and then you can copy paste. Right. I'm going to assume that most of you are in the same position as me, where you don't have the ability to do that. All right. So what we're going to do is we're just going to take this and pop it in to the home screen and replace the X with the 2.5. All right. We don't need the 80 anymore. All right. So we could also do it in the grapher, but you're going to get more information than you really need. But I will show you real quick, and then we'll go back into the home screen. I'll show you that too. All right. So, okay. Add an element. You could use f of x if you want. We're looking at 31. E, basically all the stuff I just typed in. 4 ln 26 over 31. Oops, one too many. Then I'm going to type in the X and then plus 69. All right, so basically what I just typed in the equation menu, except instead of the 80, I'm putting f of x. I hit OK to lock it in. And then you could go to the table. You can go to the graph. I'll go to the table. So up arrow, get to the table, hit OK. And you'll see, it'll give you the array of values from 0 to 10 for x. I need 2.5. And it's not just a matter of just taking 2 and 3 and averaging them together. So what I'm going to do is I'm going to go to set the interval and have it go by a step value of 0.5. And then I can go down and see where 2.5 corresponds to in terms of temperatures. And so that's going to give us about, what do they say, around to nearest degree. I'm going to write the decimal first. So about 74.339. And that's going to be about 74 degrees. All right. Which I guess kind of makes sense. although about 1.4, yeah, after about 1.4 hours, so we're in this neck of the woods for part A, that'll get us to 80. Yeah, to get us below 80, it's going to take more time. So around 2.5 hours. I guess it makes sense. You know, it's not something that necessarily is as relatable, except to say as time passes, the temperature is going to decrease. I don't know that I would look at it and say, well, of course, after an hour and a half, it'll be 89 degrees or 88 degrees. After 2.5 hours, it'll be in the mid 70s. So after like X hours, it'll be this temperature. Like that part isn't as relatable, but the idea that it is decreasing in temperature, that should be somewhat relatable. Right. And again, if I wanted to do this in the home screen, I would just type in 31 E to the 4 ln 26 over 31 close it up, then multiplied by 2.5, then plus 69. So you see the only difference between what I typed in the equation editor and what I'm doing here is I'm actually putting the real value of T in there. All right. But when you do that, it gives you the 74.339. You could round it the way they ask you to round it. And that's really all there is to it. All right. Much easier once you have the equation, but it, you know, unfortunately, it can be tricky to come up with the equation. But it's a matter of just following the model, following the process. All right. So that was the last thing I wanted to go over with you in this unit. Let me stop the recording.